I'm Lou with IT Sparkcast, and I'm here with Micron at the CXL booth and Vinicius. And he's going to talk to us today about CXL memory pooling in action, showing how CXL can actually increase your memory pool and decrease it. So can you show us that?
Sure. Yeah, just some light just for context. So here is the system setup, right? So I have 4 hosts, right? So Intel systems, and then 1 memory box. So we put the 22 Micron CZ 122 device.
So those are all DRAM memory modules.
Yes, behind there are the DRAM modules, and then on the CXL device, so connected PCIe, right? On those, the box. Also, the host also connected via PCIe interface. So, and then every host has 512 gigabyte locally that can use. And we run some workload that basically going to use more than available locally. And dynamically, the extra memory should come from the pool device. They can all share the pool device.
Okay.
Right? And then we have total 22 of our modules. That is 5.6 terabyte of shared memory in the pool that every host can take dynamically, right? When it goes beyond its local capacity, right? And of course, the provision in the local capacity depends on the average usage, right? And then the standard deviation, once they need more, should come from the pool, right? So the workload is called DuckDB, which is a database. It's a very fast, high-performance analytical database system. And the benchmark is called TPCH. It's a standard benchmark to evaluate complex analytical queries. And then to show the requirements, so here's an example of those queries, the TPCH queries, sorted by requirements. So one query for the number 9, it's a very heavy query. It needs 3.5 terabyte, right, to complete, right? This is a scale factor of 10,000, which is 10 terabyte in a CSV format, but DuckDB has a compression that goes to almost 2 terabytes of raw data, right? When it comes to memory, you need more memory to process that query. So this diversity in memory requirement demands this flexible rehandling, right? And dynamic pooling is an answer to actually satisfy those dynamic queries. So some query you can see using 256 gig, right? Some query use 512, 700 gig, up to 3.5 terabytes, right? And we demonstrate this orchestrator that we implemented as a proof of concept. Basically, every host dynamically requests chunks, right, for the orchestrator, and the orchestrator is going to manage that shared pool using the fabric manager in the switch to actually allocate the request. And then once the host gets acknowledgement and ownership for a particular allocation, then the host can online those blocks online, right? That's what we're gonna demonstrate. And how the host trigger a more allocation, less allocation is based on a simple threshold-based control loop. So we set at 7% of system RAM, so the host keeps monitoring its own system RAM, or the workload can monitor itself. As it needs more, you're gonna make a request to the fabric manager, the orchestrator, to bring more memory online. And then on the other hand, when you're not using your memory, you can then release back to the pool, right? So that's pretty much. Let's look at the example here, right? So that's we just recorded. It's a live, but we just record to be able to repeat. So what's showing here is those servers are running different queries, right? And over here is still the local memory usage at real time. And you can see that nothing is being used in the share. So the bottom here is the CX share pool, right? So every request is 32 gig of chunk, but no host is using anything beyond your local memory. Now, see, host number 1 is running a heavy query here. So you need more than 512 gig locally and start using the shared memory, the shared pool here. So every host can take a chunk of the shared pool. And as it's finished, you're going to release it back to the pool, right?
So how quickly am I going in and out of this memory?
It's very fast. So every second, you can take a chunk and then online your memory.
And my latency is what, on the order of 100 nano, 200 nanoseconds?
The memory, yeah. So it's a switch. So it adds a 1 hop. So about half a microsecond, 500 nanosecond.
Okay, so now I see the thing running up. What is the mechanism you're using? I see you're on Linux.
Linux, yes.
What are you using to manage that memory? As far as, is it NUMA or?
Yeah, it's a NUMA. Yeah, if you can see, basically, there's a NUMA 0, which is the CPU plus the local memory. And then we have a NUMA 1, a separate NUMA, that get aligned dynamically as more memory is needed, right? So it becomes like a system memory. So basically, both the memory from the local pool, which is NUMA 0, and NUMA 1, which is the extra NUMA, they are part of the same system memory. And Linux can use it as you wish, right? The workload, transparently, doesn't need to do anything. Basically, it's more memory in the host, basically, right? And then keep running, right? Now using more. Some queries are going to use way more memory, some queries less memory, but all can benefit from shared memory, right? And then if you don't have enough memory, what happens? The query runs out of memory and then crash.
Right.
Or
yeah, that would make sense.
You try to spill over to disk, but the disk will be way slower than using memory, right? That's the alternative. Now, all queries can finish faster by using memory, right?
So the audience that I'm talking to is primarily an enterprise audience that may be looking to stretch the utility of their existing servers, or buy one server that's got a ton of your memory in it and then share that out to other servers. Is that possible to do with this technology?
Sure, yes, definitely. Basically, you're provisioning your local capacity, let's say for your average utilization, for your average query. But if some queries need more, then you can always go to the share pool and then share, right? And then because it's dynamic, you don't have stranded memory. So every host is not over provisioned for the worst case. So you can provision for the average case, for example, right? Or below average. It depends on your requirements, right? It's a decision of how you manage your local capacity, what's the ratio of local versus remote memory. Some workloads are very tolerant to the latency, right? Because memory is good as any memory, right? But some workload needs more local memory than remote, so you adjust that. And also Linux has the capability to do tiering. So basically, some of these pages, when it's very hot, you can migrate pages from the share pool to the local, and you get better performance, right? Because not all pages are hot at the same time. So basically, you can do some kind of tiering, automatic.
So we're
management.
dynamically using NUMA to move these pages around.
Auto NUMA, exactly. And it has the best performance because now some of the pages that are not very accessed can still in the share pool because you're not accessed too heavily. You don't have the performance penalty, and as you need it, you can move quickly back to the top tier. Right? You can do this flux of migrations, page migrations, right? But memory is good because you don't need to swap in, swap out. If it's in the remote memory, quickly you can access it as a memory, also bring to the top tier, and have faster execution, right?
So what happens when it starts to spool down?
Yeah, exactly. So when you go down, so let's see some example here. So let's see. So these are just moving a little fast. So this is, I'm gonna move just to show you how, for example, server number 2 here, just finished the query, right? And now that's the blue, right? So now you're gonna see, now below 30% threshold, now the blue is gonna be deallocating for the pool, right? You can see some deallocation happening here. I can just move a little bit forward. I can see that the blue, right, is going to be deallocated. Let's see, so the query here, 21 finished, right? Success or return back. Now the pool memory get returned back to the pools here. So the blue is being deallocated dynamically, right? While the others still using the shared pool because they're still processing those queries, right? This query is still processing. But you can see that server 4 also be gonna finish in soon, right? I can move quickly just to see the. So here now, server 2 gone, nothing being used, released back. All this part can be reused to other servers, so all the hosts can share the same pool, right? Yeah.
Wow. Okay.
Yeah.
So in a world where you were previously throwing away servers because you couldn't get more RAM into them,
yes.
This means you can extend the life of your existing system if you wish it,
right?
By buying either a dedicated memory box with like a Titan, or a server with your technology in it, that you use to share as well.
Yes, perfect. So
that's pretty powerful.
On the Intel, but basically yes, people would scale just because they need more memory for a database. Let's say, oh, let's buy another server because now you get more DRAM. But no, with a memory pool, stick with that server. It has enough cores, there's computing power. And now JBOM, this is called like a just a bunch of memory.
Yeah.
And you stick in all these things, and there's some things there as well.
Yeah.
And then the big improvement are these DCDs, what we call dynamic capacity device, meaning before with this CXL technology, the original JBOM concept was introduced in version 2.0. Then in version 3.0, they did a little enhancement whereby in 2.0, a server got assigned a fixed chunk of memory. Okay, be happy with it, right? So it's got its own DRAM, now it got a chunk from JBOM, but it couldn't add anymore. It can only fully give it up, right? Once it was done execution of that workload. With this, while it's executing, it can say, imagine like a Word file where you keep on adding data. Now the file keeps on growing. Originally, your laptop OS didn't allocate it so much memory, but as you request more, it keeps on allocating somehow from the local memory. Here, you can do that with the JBOM. That's really what we are showing.
Yeah.
Right? As these servers are ramping up, their memory consumption goes up. Dynamically, it goes to the pool, consumes the memory. Of course, there's still a limit, but at least now
It's much higher.
Yeah.
It's much higher. And folks, that was Anil from Intel who came in to talk as well with Micron. This is a dual Intel and Micron demonstration. And this is IT SparkCast from the show floor of SuperComputing 25.